Okay, now what we're going to do is we're going to graph two more rational functions. We're going to pick out x-intercepts, vertical asymptotes, horizontal asymptote, and holes, if any. So our next example, we're asked to graph the function 4x squared divided by 2x plus 8. Let's start by finding the x-intercepts. Now remember that the x-intercepts are going to take place wherever the numerator is equal to 0. So what makes 4x squared equal 0? 0 would. So that means that I have an x-intercept at 0. Okay, so when I plug in 0, I get 0. Move my face out of the way here. So 0, 0 is going to be a point that's on my graph. The next thing I look for is any vertical asymptotes. Well, the vertical asymptotes take place wherever the denominator equals 0. So if I think about setting this equal to 0 and solving it, I'd have 2x is equal to negative 8. And when I would divide by 2, I would end up with x is equal to negative 4. So negative 4 is a number that I can't plug into the denominator. So I would draw a dashed line at negative 4. Scroll down a little bit here. This is the guy that's not going to work. Now from here, I would look for, I'll put this in, any horizontal asymptotes. Well, that depended on the degree of the numerator versus the degree of the denominator. This one has a degree that's greater in the numerator than the denominator, which means, according to our rules from before, that the graph has no horizontal asymptote. Instead, the graph's end behavior is the same as the graph of a sub m over b sub n, meaning the leading coefficients of each polynomial, times x to the m minus n power, where m is the degree of the numerator minus the degree of the denominator. I'll show you what it looks like. So there's none for horizontal asymptotes. Instead, we're going to have a slant asymptote. How to do this? Basically what I'm going to do is I'm going to take these first two terms, 4x squared over 2x, and I'm going to think about what would happen if I were to divide them. Well, 4 divided by 2 would be 2, and x squared divided by x would be x. So 2x is a slant asymptote for this function. Now, again, I don't necessarily know, you don't have to know that exact equation, but I want you to take a look at what it looks like if I graph that using Desmos. So, I'm going to face out of the way again. Here's what this function looks like when I type in 4x squared divided by 2x plus 8. Now notice you got this one branch here. If I pull this up a little bit, you'll notice that negative 4, that was our asymptote. That looks like that's holding true. Now, the weird thing is, again, I also have an intercept at 0, 0, which is great because that made the numerator equal 0. Now, I don't see a second branch. Well, to see a second branch, I'm going to zoom out and pull this up a bit. Notice that the second branch is way down here. Now, it's still holding that x equals negative 4 is my vertical asymptote, which is good. Now, notice how the graph sort of curves down and to the left, and this one curves and goes up to the right. Well, I said that our slant asymptote was y equals 2x. Watch what happens if I were to graph y equals 2x as a function. Here, y equals 2x in purple. Notice how the end behavior matches up. This graph is going down that way, and up here it's headed up in that same sort of direction. Okay, so the end behavior of my graph matches the end behavior of the function 2x. They basically look the same as x goes to positive infinity and negative infinity. Kind of a neat thing to take a peek at. So that would be an example of a graph where the numerator has greater degree than the denominator. And one more example to look at. And that would be when my numerator's degree is the same as the denominator's degree. Both of these have x squared in them. So let's think about this. First of all, where are the x-intercepts? Well, whatever makes the numerator equal 0. Now, not quite as easy. I know this is a quadratic expression, and you're probably going to want to reach for your quadratic function or quadratic program, I know. Instead, what I would say is I would encourage you to factor this, and you'll see why in just a second. If I factor the numerator, I have x and x, and then I need factors of positive 1 that add up to negative 2. Well, that'd be negative 1 and negative 1. Okay, those are the factors of this polynomial expression. Come back to that in a second. I'm also going to factor the denominator while we're in the factoring mood. I have x and x to begin it. I need factors of 3 that add up to negative 4. That'd be something like negative 3 and negative 1. Now, notice this. This helps me in a couple of ways. First of all, when I identify x-intercepts, now I can easily tell what makes the numerator equal 0. It's 1. Plug in 1 and make either one of these factors equal 0. So I could put a dot on my graph at 1, 0 right here. Okay. Now, as far as vertical asymptotes are concerned, I look at what makes the denominator equal 0. Well, that's pretty easy too, because I've got it in factored form. I can easily pick out the fact that 3 and 1 both make the denominator equal 0. So I would think that based on that, I might have vertical asymptotes at both of those places. However, only one of them is actually going to be a vertical asymptote. Okay. Now I'm going to show you the graph here in Desmos. Here I've got the graph in green. Notice that as you look at this, it seems to be only one vertical asymptote. That vertical asymptote looks like it's at, this looks like it's at 3. Okay. Now, based on our work in our equation, we think that there'd be a vertical asymptote at 1. But I don't see a vertical asymptote at 1. Instead, I see my curve being connected there. Interesting. What's happening here is I have a shared factor in the numerator and the denominator. I have x minus 1 as a factor in the numerator and x minus 1 as a factor in the denominator. What that means is instead of having an asymptote at 1, I have a hole at x equals 1. Not a vertical asymptote, but a hole at 1. Okay. Here's what that means. If I were to take a look at my graph, you'll notice how it's connected. It looks like, when I plug in 1, I get 0. That's interesting though, because if I plug in 1 squared minus 4 is going to be negative 3 plus 3 is 0. You can't actually plug in 1. So even though I said x equals 1 is my intercept, and it looks like it is, instead of actually existing there, there's a hole. So here's how I would draw this. I'm going to put a hole at 1, 0. Now, we said that there was a vertical asymptote at 3, so I'll draw my vertical asymptote. And when they're the same, horizontal asymptote, we'll throw it on there too. Horizontal asymptote is going to be at y equals 1, because when they have the same degree in numerator and denominator, again, I would divide the first two terms. So x squared divided by x squared equals 1, which is why that's our horizontal asymptote. So if I draw that in at 1, I could draw the branches of my graph. They look something like this. First quadrant and over, and then the third quadrant, and down with a hole at 1, because I can't plug in 1. But it's not an asymptote because it's a shared factor in the numerator. Okay? So anytime there's a shared factor in the numerator and denominator, we're going to have a hole. So that's why, again, when the graph looks a little bit different than we might have expected it to, but works out okay. You'll notice too, where's my horizontal asymptote? Looks like we're getting closer and closer to 1 on both sides, with a vertical asymptote at 3, just like we predicted, and a hole at 1, 0. Try to click on it. Yeah, it says it exists, but in reality, it's not actually there. So that's looking at graphing some general rational functions, finding vertical asymptotes, horizontal asymptotes, x-intercepts, and holes. Good luck.